Okay, let's get started. Thank you everyone for making it in on time. You made a big mistake by coming on time because now I know you can come on time. All right. So I'll hold you to it forever. All right. So welcome back to Service Security. We are now in week 8. All right. Wow, 8 weeks have gone by. Time to start writing some Rail code. All right. Not that the code you were writing so far isn't Rail, but it was for assignments. We're going to start working on the projects from this week. Okay. All right, cool. So we're done with we finished last week with the cryptography module of this class. So we spent 3 to 4 weeks just talking about crypto technologies. Okay. That was after a few weeks of introduction and to security, information theory, error checking, so on. All right. So we're now kind of entering the major segment of this class, which is going to be about secure application developments. All right. However, to do that, we're going to spend this week and the next week just talking about basic infrastructural things, about how the system we're going to make, like some basic building blocks. Starting this week with web APIs, and next week will be databases. For those of you who have taken my SOA class before, this week and next week will feel like a bit of a repeat of what I did in the last or next semester. But maybe with 1 or 2 new things, all right? But then after that, we're going to fall into more specifically security-related things. So, all right, so bear with me. Okay, so this week we're going to talk about HTTP. All right, I think you all have some sense of what HTTP is all about. What is it? Briefly. Yes, I know. Yes, hypertext. The professor can't read anymore. Call the doctor. His hypertext transfer protocol. What is it used for? For websites, right? But it's not the language in which you make websites. It's not HTML. What is HTTP? Transferring hypertext. A protocol to do it by any chance? How the data is sent across the internet to the web browser from the web server, something like this, right? Okay. So is HTTP part of internet? Right? Is it? It is. What's the relationship between the two? What's the difference in saying, hey, I'm going to use HTTP versus I'm just going to talk over the internet? There's different protocols? All right, okay, we're getting there. Thank you. All right, the coffee's kicking in, huh? All right. Okay, let's take a little look at how, oh yeah, please, Brian. You raised your hand? No? Okay. All right, so I want to talk a little bit about what HTTP gives you and what it doesn't give you, all right? Because this is a security class, so we should be kind of aware if HTTP has any security provisions in it. Some of you probably, no, almost all of you know that there's also HTTPS, right? So what is HTTP? Like a non-secure HTTPS? All right, so let's talk a little bit about what it is. And to give you a sense, I also want you to kind of have some understanding of where this all comes from, all right? Because the people who made these protocols to talk over the internet, they had something in mind. In fact, they had a major security consideration in mind. But it may not be the security considerations we have in mind today. So let's talk about what it is that the internet kind of gives you in terms of security and what it doesn't give you in terms of security. Because if the internet if all these protocols give you security, then we don't need this class. We can just pack up and go home, right? But we'll try to see what it doesn't give you as well. So so let's start by talking about the protocols on which internet applications and things are working on. Not all of them, but a couple of them in particular. And I'd like to give you a little view of where it comes from So I'll show you a little video, all right? I'll show you a little video. It's video time, yay! And um, as you're watching it, I want you to, if you have a piece of paper in front of you, or somewhere to take a note, or Brandon, in your head, all right? I'd like you to kind of ask yourself or answer the following questions, all right? One is, what is the major threat that the people designing early internet were concerned about? What was the major security threat they were concerned about, or threats? The second thing is, what are the kind of building blocks of the ways in which we communicate over the internet, all right? And all right, so with that, let's kind of take a little peek at this video, all right? Let's see if I can make it full screen, and it should hopefully have some audio component to it. Are you guys ready? You ready for a video? Yeah, always ready for a video.
The internet.
Whoa.
In the year 2009. We send emails.
This is 10-year-old video.
The internet and discuss topics we take an interest in. Even our banking is going virtual. But what we take for granted today was only a vague idea 50 years ago. In order to understand how we got this far, let's go back to 1957, when everything began. Before 1957, computers only worked on one task at a time. This is called batch processing. Of course, this was quite ineffective. With computers getting bigger and bigger, they had to be stored in special cooled ROMs. But then the developers couldn't work directly on the computers anymore. Specialists had to be called in to connect them. Programming at that time meant a lot of manual work, and the indirect connection to the computers led to a lot of bugs, wasting time and fraying the developers' nerves. The year 1957 marked a big change. A remote connection had to be installed so that the developers could work directly on the computers. At the same time, the idea of time sharing came up. This is the first concept in computer technology to share the processing power of one computer with multiple users. On October 4th in 1957, during the Cold War, the first unmanned satellite Sputnik 1 was sent into orbit by the Soviet Union. The fear of a missile gap emerged. In order to secure America's lead in technology, the US founded the Defense Advanced Research Project Agency in February 1958. At that time, knowledge was only transferred by people. The DARPA planned a large-scale computer network in order to accelerate knowledge transfer and avoid the doubling up of already existing research. This network would become the ARPANET. Furthermore, 3 other concepts were to be developed, which are fundamental for the history of the internet. The concept of a military network by the RAND Corporation in America. The commercial network of the National Physical Laboratory in England. And the scientific network Cyclades in France. The scientific, military, and commercial approaches of these concepts are the foundations for our modern internet. Let's begin with the ARPANET, the most familiar of these networks. Its development began in 1966. Universities were generally quite cautious about sharing their computers. Therefore, small computers were put in front of the mainframe. This computer, the interface message processor, took over control of the network activities, while the mainframe was only in charge of the initialization of programs and data files. At the same time, the IMP also served as interface for the mainframe. Since only the IMPs were interconnected in a network, this was also called IMP subnet. For the first connections between the computers, the Network Working Group developed the Network Control Protocol. Later on, the NCP was replaced by the more efficient Transmission Control Protocol. The specific feature of the TCP is the verification of the file transfer. Let's take a short detour to England. Since the NPL network was designed on a commercial basis, a lot of users and file transfer were expected. In order to avoid congestion of the lines, the sent files were divided into smaller packets, which were put together again at the receiver. Packet switching was born. In 1962, American Ferret aircraft discovered middle and long-range missiles in Cuba, which were able to reach the United States. This stoked fear of an atomic conflict. At that time, information systems had a centralized network architecture. To avoid a breakdown during an attack, a decentralized network architecture had to be developed, which, in case of loss of a node, would still be operative. Communication still used to work through radio waves. That would have caused problems in case of an atomic attack. The ionosphere would be affected and the long-wave radio waves wouldn't work anymore. Therefore, they had to use direct waves, which, however, don't have a long range. A better solution was the model of a distributed network. Thus, long distances could be covered with a minimum of interference. Another milestone followed with the development of the French network Cyclades. Since Cyclades had a far smaller budget than ARPANET, and thus also fewer nodes, the focus was laid on the communication with other networks. In this way, the term Internet was born. Moreover, Cyclades' concept went further than ARPA's and the NPLs. During communication between sender and receiver, the computers were not to intervene anymore, but simply serve as a transfer node. Cyclades' protocol went through all machines using a physical layer that was implemented into the hardware, providing a direct connection with the receiver, an end-to-end structure. Inspired by the Cyclades network and driven by the incompatibility between the networks, their connection gained in importance everywhere. The phone companies developed the X.25 protocol, which enabled communication through their servers, in exchange for a monthly basic charge, of course. DARPA's transmission control protocol was to connect the computers through gateways. And the International Organization for Standardization designed the OSI reference model. The innovation of OSI was the attempt to standardize the network from its ends, and the channel's division into separate layers. Finally, the TCP assimilated the preferences of the OSI reference model and gave way to the TCP/IP protocol, a standard which guaranteed compatibility between networks and finally merged them, creating the Internet. By February the 28th, 1990, the ARPANET hardware was removed, but the Internet was up and running.
All right, video over. So, question time. Hold on, let me just put earphones on so that folks at home can hear me a little clearer. Okay. Yeah, still connecting. Okay, so I want to talk a little bit about what we're seeing here and what it's talking about. Okay, so first question to you is, hold on a second. Hold on, let me see if I can connect to my AirPods or not. Don't know why it's taking so long. Maybe no AirPods today. We'll see. All right, so one question I have is, what was the major threat that people were thinking about when it came to designing the internet? What were they mainly worried about in terms of security? It may not be a threat that we've talked about in class. What was it? Atomic attacks, right? So They were more worried about creating some kind of system whereby people could communicate, and if one node in the network went down or got destroyed, the communications could still go on, right? So their main emphasis was on getting the signal across to the other side, even if there's disruptions in the middle. So rerouting the packets any way that they could, right? Okay, so that's kind of interesting. You notice this whole video, they didn't mention, what did they not mention? What other aspects of security did they not mention? In fact, they didn't mention any of the aspects of security we talk about in this class. They didn't talk about authentication, they didn't talk about authorization, they didn't talk about data integrity, but data integrity probably is in there in some ways. We'll take a look, all right? And then, so essentially they described a set of protocols, the different protocols that were developed over time to enable reliable communication over the internet, all right? And in particular, they mentioned TCP/IP as a protocol. So let's take a look at what this TCP/IP business is about, okay? So all the messages that are being sent over, not all the messages, but many, maybe most of the messages being sent over the internet are riding on this protocol called TCP/IP. Okay, before I get into that, the P, protocol, what does that even mean? What's a protocol? An agreed way to structure your messages, right? Do you use any protocols when you're talking in day-to-day life? Yes? Can you give me an example of a protocol you use? English? Well, English is a language, all right? But protocol is more about the structure of the communication. Speak or what you say, in which order you say things. Am I talking about grammar? Maybe at a very low level, potentially. But let me try to give a specific example. If somebody calls your phone, Bijan, your phone is ringing. You answer it how? What do you say? Hello. Hello. Way. Right? Why do you say that? I mean, if you didn't say that, wouldn't the rest of the communication be just the same content? Like, isn't that kind of a useless word to say? Why do you say that in the beginning? Establish connection. Mom, I'm trying to establish connection. Just say hello. All right. Yeah, I mean, I guess part of the reason we're saying that is so the other side knows that we can hear them, or is asking the other side, actually, can you hear me? Right? It's in Zoom, we don't really say hello. We Zoom or Google Meet, or Skype, you start the communication by saying, can you hear me? That's what hello is supposed to be. All right? Hello is like, here's my voice. You say hello, so that we both know we can hear each other, right? That's a protocol. That's the way that's an agreed upon way to begin a conversation, all right? And we also have an agreed upon way to finish a conversation. We say, bye, peace. All right, and you don't just hang up before you say that. Actually, I know some people who do, but you don't actually hang up before you say that, so that both sides know we are finished now. One side isn't still there talking on the phone. All right. Anything else we do? Let's keep talking about phones for a moment. Then, any other protocol we use when we're talking on the phone or in person? Well, a very basic thing is that we take turns speaking. We don't both just talk at the same time. Like you say something and you wait for the other side to kind of hear you and respond back to you.
It depends. If you're in Latin America, that's not true.
You just both keep talking at the same time.
No one's listening.
No one's listening. I'm not calling you to have you listen. I'm calling you to talk. Okay. All right. My AirPods are out of battery today. Out of juice. Okay. So these are protocols. This is a protocol. It's the structure in which you speak, and the things you communicate so that the other side knows that everything's going smoothly. All right. It's separate from the content of what you're speaking. All right. So I want to be clear about that. When we talk about protocol, we're not talking about what you are saying, but we're talking about how you're saying it so that the two sides can maintain a smooth conversation. All right? So a lot of the packets going over a lot of the information going over the internet is going over this protocol called TCP/IP. All right? And there are other protocols which I might mention briefly, but TCP/IP is essentially refers to a protocol in which, so first of all, remember one thing they mentioned was packets. So when you're sending a message over the internet, it isn't just like an unbroken stream of data going over. Actually, your communication over the internet is broken into little chunks, and these chunks are sent one at a time. Okay? And the reason we do this is that if there is a problem, you don't just lose the whole conversation, you just lose a little bit of the conversation at a time. Okay? So if you have a communication going from, a message going from one computer to the other, it's broken into multiple packets. So here you will see each of these tall rectangles as one packet. One packet, okay, one packet. So there's 3 packets going across here. And each packet has in it multiple layers of information. Okay, there's an IP layer, there's a TCP layer, and in the case of web communication, there's an HTTP layer, right? Okay. I'll talk about TCP IP in a moment, but HTTP, which we'll spend a lot of today talking about, well, that's for web communication. What other protocols are you aware of for application communication? So HTTP is specific to web applications. For other types of applications, do you know other protocols that other applications use? Telnet. Yes, Telnet is a protocol for terminal communications. So from your terminal's window to connect to another server's terminal. All right, so that's Telnet. So you would have IP, TCP IP, and Telnet sitting on top of it. Okay. Any other protocols? What's that? Bluetooth. Right. I don't think Bluetooth operates on TCP IP though. It's a protocol of its own. As far as I know, it's a whole protocol of its own. Because Bluetooth does not need to go over the internet. It's just device to device, right? So it doesn't need TCP IP. So let me clarify. What are the protocols you think suspects sit on top of TCP IP? What's that? MQTT. What is that used for? IoT devices, yeah? Yes, it's for messages, right? So, and I think potentially some message queues also use MQTT as far as I know. Or there's another one, I forget what it is, XM, I can't remember, okay. So, do not disturb until this evening. Huh? Yeah, there we go. All right, anything else? What's that? UDP is not an application protocol. Actually, UDP is something like a substitute for TCP/IP. Actually, it's a substitute for TCP. All right, maybe I'll talk about that in a moment. Application protocols that instead of HTTP. All right, SMTP. SMTP. What does that use for? Email. Yeah, your email application talks to the email server, not over HTTP, but SMTP. Unless you're using like Gmail and you're doing it over the browser. If you're using it on the browser, then your browser is still using HTTP because it's a web application. But if you're using like a specific mail application on your computer, it's usually talking over SMTP. All right.
I noticed there's another one called JMAP.
IMAP?
JMAP.
JMAP for email?
Yeah, like sending your email in a JSON.
Oh, okay, interesting. I didn't know this. There's also so apart from SMTP, there's another one. I think is it IMAP or POP? Oh, okay, yeah, POP is another protocol, right? Okay, yeah. And any others? I guess you guys haven't been. You're not my generation anymore. What is one way people used to send files to each other? FTP, yeah, file transfer protocol. All right, and that's another application level protocol that's on top of TCP/IP. All right, so as you can see, when you're using an application, the content, it's not going on the TCP layer or the IP layer. The content is in the application layer, like HTTP, FTP, SMTP, Telnet, etc. All right. So if HTTP, which we're going to look into deeper, is like the web content is going over the HTTP part of the protocol. So once again, your web communication, the message you're sending over the web is broken into packets. Each packet has a little bit of the content, okay? So HTTP is part of it. So then what is TCP and IP? What is that good for? So let's take a look. Let's take a look at what TCP and IP do. All right. So here is an example of some of the protocols. So every packet is split into an IP layer, TCP layer, and application layer. The application layer part of the protocol, that's your HTTP, FTP, Telnet, DNS, POP3, IMAP, yes, et cetera, et cetera, et cetera. All right. And what about TCP and IP? Well, if the application content is in the application part of the layer, then TCP is the transport and IP is the internet layers. What do they have? Let's take a little breakdown of what is in the TCP layer. Okay, if I stop a packet going over the internet, going through my computer, and I say, what's in the TCP layer of the packet? It would look something like this. All right. You have so in the TCP layer, you have all this information in the TCP layer. Okay. For example, we'll talk about ports, but it talks about from one computer to the next. Maybe do I have a picture here? So from one computer to the next, when I send my message to the other computer, which port on that computer should receive it? Okay. So you can think of ports something like, where else do we use the word port? What does it mean? Airports. Or like, Taipei has a port, Kaohsiung has a port. Does Hsinchu have a port? Not sure. Yes, maybe no. Little tiny one? Okay. So ports are basically not the country you're going to, but like the station in the country you're going to enter through, right? So similarly, on your computer, different applications are listening on different ports, all right? What's going on out there? All right. So different applications are listening on different ports so that they're not all listening to the same traffic all the time. So for example, HTTP or web communication is typically, not always, but typically over port 80. Okay? It's one of the ports on your computer, so applications that are interested in web traffic can listen to port 80 for all incoming web traffic. All right? FTP, port 21, etc. So in the TCP layer, we are told what port is the communication coming from on the computer that's sending it, and what port is it going to. All right? But you'll notice here, it doesn't tell you which computer it's going to. So TCP kind of assumes that that you already know which computer it's going to, but once the computer has received the packet, which port should handle it. All right? There's also a sequence number. Anybody want to guess what this is? The order, yeah. Because remember we said your communication is broken into packets and the packets are sent individually. There is a chance that the packets don't arrive in the same order in which they were sent. All right. Why? I don't know. Maybe halfway through the communication, it was rerouted in some way. All right. So the sequence tells you in this message which packet number is this. So you can stitch the packets back together the way you got that was sent. Okay. And some other information here. Do you notice something in here that is kind of related to something we talked about before in the beginning of the semester? Checksum. Guess what that is for? It's it's some kind of algorithm. It's some kind of number or data that was produced that captures all the information in the TCP layer so that you can detect if it has been changed by accident, like over the internet if something got changed. Okay. So, interestingly, some kind of data integrity is built into these protocols. Okay, data integrity is built into these protocols. All right. Then there's the IP layer. What does the IP layer have? It also has a checksum. Cool. But it's got a few other things, like some big things, like source address and destination address. This is like which IP address is this message coming from, which IP address is this message going to. All right. So the IP part of the layer is not really meant for you. Well, it's used by your computer as well, but it's also used by all the other machines in the middle, all the routers and gateways in the middle on the network, on the internet, trying to figure out where to send this packet. All right. So the IP layer is kind of used by everyone else other than your machine to figure out where it's going to. All right. But your computer will look at this IP layer for some information, presumably, like maybe the protocol. Like which application protocol are we going to end up using, all right? It's got to check some as well. What is that? That sounds scary. Time to live. Is it saying, don't be so boring, get out there, be alive? What is it saying? Yeah, it's how long can the packets stay on the network? So remember, these packets have been sent from one machine to the other, or one router or gateway to the other, going around the internet. What if it goes in a big circle, comes back to the same router that sent it out before, and just going around the internet forever? That would be crazy, right? So time to live is basically saying how many more hops can this packet make before we just kill it, because it's made too many hops on the internet. Okay, so it could be like a large number, and every machine that gets it just subtracts one from it or something like that, so that by the time, if it's been on the internet for too long, just going around machines, at some point it'll get to 0, and somebody will say, that's enough, let's kill this packet, it's not going anywhere. All right, so that's the time to live. All right. So this gives you some sense of what the TCP and the IP layers are doing. The IP layer is really trying to get the packets of data to you from the source. The TCP layer is more about, once it's come to your computer, who should handle it? Which port should it go to? All right? And the sequence number also tells your computer how to stitch the packets back together into the original message. All right? So any quick questions about this? So this is about TCP IP aspect of the internet, all right? And as you see, it's mainly concerned about maybe data integrity to some degree, but it doesn't really care much about the other dimensions of security that we've talked about in this class. These are not necessarily really very important things in the early internet protocols. So if TCP and IP don't give you any of these things, guess who's got to do it? Probably the application has to do it by itself. Every application has to do all these things by itself, okay? And this is maybe potentially one of the downsides of like the structure of the internet, the way we've had it so far, is that there's not a whole lot of security guarantees built into it, apart from just getting the packets to you and making sure they didn't get changed too much, all right? Okay, cool. So once the packet arrives, once all the packets arrive, they're stitched together. So then the HTTP layers, all of this is put together so that the message, the web message is kind of understood. Okay, once all of these are stitched together. Okay, so let's talk about before I go on, there are other alternatives to TCP/IP. The IP layer is kind of standard, so that you know how to get the packets to the other side. So the IP layer is kind of standard, but the TCP layer is not standard. There's some applications that could potentially use things like UDP, and UDP is an alternative, is something other than TCP, and essentially, as far as I know, UDP is essentially a way of just making sure that the packet gets to the other side. You're not really looking for an acknowledgement that everything has happened, okay? So if you just want to blast packets to another computer, you don't really care if it gets there or not so much, or you're not really so much caring about the content, then you use something like UDP, all right? Where you don't really necessarily need to stitch packets together to make a message, a big message. You just want to get individual packets out there, all right?
I think that's what live stream uses.
Maybe, maybe not. I'm not entirely, okay, do you know this for a fact? Potentially, but I'm not sure about that entirely. I think it still uses TCP/IP, as far as I know. But maybe you can find out and let us know on Slack if you discover that. Okay. So some simple things that use UDP is like the traceroute function. This is a little command that you can use on your computer just to blast packets to another computer somewhere, just to find out what is the route that the packet took. All right. But you're not really trying to send a specific message. All right. ICMP is another one That's used by when one of you ping another computer to see, are you alive? But there's no real message you're sending. You're just sending a packet to say, are you alive? If so, tell me you're alive. That's it. All right. You don't need to string together a big message. All right. But typically, when you're trying to string together a big message, you're typically using TCP over IP. And then you have an application layer on top. So let's talk about the application layer. So in our case, we're using HTTP. So once the packets come to my computer, or the packets are put together, and then the HTTP message is extracted. All right. Let's talk about HTTP. So HTTP is a way of packaging the message for a web application. All right. And there's a few things I want to just mention about HTTP before we look into what it actually look like what is the content of HTTP. All right. But there's a few things I want to just kind of mention. There's a couple of different types of HTTP connections. Some are called in some connections, when a message is sent to the server or it comes back. Okay, so let's say a client like your browser sends a message to the server saying, please send me this web page. And the server replies. In some cases, as soon as the reply comes, the connection is closed. All right. But in other cases, HTTP can actually specify, don't close the connection. I may have more things I want to ask you. So a connection can be kept open. All right. What's the difference? The difference is if you close the connection, then the next time you send a request to the same server, you've got to again find out, okay, which route do I take through the internet? How do I find that computer? You got to do all that again. You got to go through the whole procedure of going through the internet to figure out which path to take to find that server. All right. But if you know that a browser is talking to a server and it's going to ask for the web page and several images and many things, it'll just keep the connection alive for some period of time so that it doesn't waste time trying to find that server again. All right. So one thing about HTTP is that it can be a persistent connection, meaning that you actually, once you found the server, you are in direct communication with it, and you don't have to go through this whole process of trying to find it again. All right. So that's good, and that's an advantage of HTTP. However, there is something else about HTTP which is going to bother you for the rest of this semester, which is that it is called a stateless protocol. This means that if your browser is talking to a web server, the protocol itself does not keep any memory of the conversation. All right? So if a browser sends a message to the server, as far as the server is concerned, it's the first time it's ever met that browser. It might be actually the 100th time in the last 1 hour that the browser has made a request to the same server, but to the server, every request is like the first time they're talking, ever. All right? So there's no memory in this protocol, which means that if you want to maintain a user experience, so let's say Steven is using an application that I wrote, every time his browser contacts me, I have no idea who he is. I don't know that this is Steven. I cannot even say, hi Steven, welcome back, because I don't know who it is. If I want to create an experience where I'm like, hey Steven, good to see you again, we just talked 1 second ago, right? Then I have to somehow hide this information somewhere and make sure that, or I have to somehow get Steven's browser to inform me again that this is Steven, he just talked to you like 3 seconds ago, all right? The HTTP protocol does not have something like this built into it. It's stateless. It has no idea. Every message is like the first time it's ever getting a message from that client. All right. So that's why when we're going to be writing code this semester, we're going to have to put a lot of effort to maintain some kind of experience for the user, where the user feels like, yeah, I have a shopping cart. I'm adding things to my shopping cart. It's not built into HTTP. You have to create this thing called a shopping cart and somehow hide information here and there so you can figure out when somebody comes back to you that, hey, yeah, it's Steven, he had a shopping cart, he had some things he was already buying, all right? Or, for example, Stephen is logged in or he's logged out. This is not part of HTTP. Your web server, your web application has to kind of create this experience by itself. All right? So HTTP is a stateless protocol. All right? Any questions particularly about the stateless aspect of it? Does anybody not understand what it is or have any questions about it? All right? Okay, you're all right for now? Okay. We'll definitely see this more and more as the semester goes on because a lot of our coding is around the stateless problem of HTTP, all right? And how do we kind of maintain an experience so people don't feel like, hey, I just talked to you 3 seconds ago, you forgot who I am? Yeah.
I noticed there's also stateful. Could you give an example?
Where yeah, okay. So there's different protocols. Some are called stateful, some are called stateless. And I won't go into the exact details, but in some protocols, they can keep the protocol itself has a place to store some memory of like the previous conversation that we had, all right? Not the whole conversation, but some important aspects of the conversation that we've had. So TCP, other low-level internet protocols like BGP. BGP is actually the protocol that the main gateways on the internet use to communicate with each other, all right? Do you have a picture here? So BGP is not used between your computers and the local area network. It's often used at a much more low level within the internet to connect major clusters together. All right. So some protocols do actually maintain some limited information about the conversation. Maybe at least simple things like who is it? Have we talked before? What have we agreed upon before? Some things like this. Okay. But HTTP does not. As far as every HTTP message has, by default, it has no information about previous messages. Okay. If you wanted to have information about previous messages, you have to engineer that within your application to add that as part of the content that you're sending over. All right. I'll try to show you some more concrete examples of what I mean by stateless a little later in the semester. All right. But that's a good question. All right. Okay. Okay, moving on. So we talked about, we talked about TCP, we talked about IP. All right, so just a reminder then, every packet coming over, it's IP with some TCP, and then the application data, which in our case is going to be HTTP. And it goes into, and protocols typically are linked to a particular port, right? Okay, so this is like the building blocks of the internet. And from this, we want to build an application where people can access us, in our case, as a web application using a browser, though potentially it could also be a mobile app because a lot of mobile apps also talk to servers using HTTP. All right, so HTTP is not limited to just web browsers. Other kinds of devices can use HTTP as well, on top of whatever protocols they're already using. All right. So essentially this semester, we're going to start, this is not the full architecture, but this is a basic idea of the architecture we're going to be kind of creating for our web applications this semester. All right. So let's kind of break down what's added. So I'm calling this an API-centric architecture, and I'll kind of try to explain what that means. All right. So first of all, we're going to make a web application, right? So our web browsers are going to be part of our architecture. Any user coming in is talking to us typically over a web browser, all right? But not necessarily only a web browser. But let's start with web browsers. Okay, they're going to talk to us with a web browser. What are they going to talk to? Who are they going to talk to with a web browser? Well, they're going to communicate with a web application. So we're going to have a server eventually, not this week, which is going to be a web application, meaning it's going to serve content for browsers. What that means is that what the web application has to send back to the browser is some information about not only what to show on the browser, but how to show it on the browser, what colors to use, how to lay it out, the whole design of the web page and all that stuff, right? Okay. What language do we typically use? So this is going to be the content of the HTTP is going to be, the body of the message is going to be something that browsers can use to say, oh, this is the content I have to show the user, and this is the layout. This is how to kind of organize it on the screen. Okay. What language do we typically use to define the content and layout of a web page? HTML, right. So the web application will send back, the web browser and the web application server will talk in HTTP, but within the HTTP, the content will be in a language called HTML. Are you clear about that so far? Okay. So HTTP is just a protocol on how we speak, but it's not the content of what we speak. The content is usually also in some kind of syntax that the other side should recognize. So in this case, it'll be HTML. Cool? We are not going to start with this week. Okay, we're going to make this some other week. All right. So because there's some more fundamental stuff we want to build before we make the web application itself. All right. And the reason is for a couple of things. Well, one reason is not everyone who's going to talk to our application is necessarily a web application. We would like to have the option one day of having, let's say, a mobile application talk to our servers as well, right? And a mobile application typically will not talk to a web application because, why? Because a mobile application is a lot smarter than just a browser. Your web application already knows how to show it on screen. It doesn't need like HTML. It doesn't need to be a mobile application does not need to be told how to put everything on the screen, what color to use, etc., etc. All that information is already known to the mobile application. That was coded as part of the mobile application. So the mobile application only wants the data. It tells me, just give me the content. Don't give me like HTML and CSS and tell me how to design things. The mobile application has its own design for the front end. All right? So notice I'm using the word front end. By front end, I'm just talking about the devices and software that runs not on your servers, but on the user's machines, okay? So for example, the browser is what I would call front end because the browser is running on the user's machine. It's not your machine, you being the service provider, okay? The mobile application, it's not running on your computer, it's not running on your servers. The mobile application is running on the user's devices, okay? So these are what I'm calling front end, all right? So what would a mobile application talk to if it doesn't talk to a web application? Well, it will talk typically to something we call a web API. All right? And an API is a lot like a web application, except it only sends the content, the data. It does not send much or any formatting information. So the difference between the web API and the web application is whereas the web application will tell, for example, a browser what content to put on the screen and how to lay out the content, the web API only sends the data, the content itself, all right? So typically, though not always, but typically the web browser will not talk directly to the web API, even though the web API has the data it needs, because the web API will not tell it like the design to use to show the content, all right? The mobile application will use the web API because it doesn't need to be told the layout and stuff. It just needs the data. Are we good with this so far? All right? Okay. Now, often, to avoid duplication, the web application does not actually have access to the data it needs to send to the user, because the web API already does that job, right? It's usually the web API that talks to like the database where the data is stored. So usually, again, but not always, but usually, when the web application wants data to show to the user, it doesn't talk directly to the database, it also just talks to the web API and says, yeah, there's a web browser asking me for stuff, could you give me the actual data? And then I will make it look pretty in HTML and send it to the user, all right? So this stuff, the web application, the web API, the database, this stuff is running on the service provider's machines, right? So if you're a company, it's running on your company machines. This is typically what we call the back end, all right? This is server-side software and server-side hardware. Any questions about this general architecture I'm drawing? This does not have to be the architecture that every company uses, but I'm just showing you one relatively clean idea of what we're going to be developing this semester. This is not an architecture class, so I'm not going to like entertain much debate about how to create the architecture, but more about the security within these layers. Any questions about this, or any thoughts, or anybody has seen this or seen an alternative you want to mention to me? Anybody? No? Okay. All right. So this is the simple view of the architecture we're going to develop this semester. We are not going to make a mobile app unless your team wants to do it by yourself, but I'm not going to be talking about mobile apps. But we have a web API, so you have a place that mobile apps could talk to get the data they need. All right? Yeah.
So would web API be like the PHP part of the web application, and then the web application part is like whether you use Angular or HTML?
No, good question, good question. No, actually, the web API and the web application, they are, let's say, the PHP part of your application. They serve up raw HTML. They do not run any JavaScript unless the server happened to be written in JavaScript, okay? They are running stuff that's, like you said, in PHP, Java, whatever language. In our class, we'll be using Ruby, but it would be those languages, okay? The only difference is the language in which it is sending, what it is sending out, and how the syntax is sending it out in, okay? So for example, the web API, since it's sending data, how do you think it typically packages the data? Like, what format do you think it puts the data in? JSON, something like JSON or XML, all right? So the web API typically takes requests and just sends out JSON or XML, just data, all right? The web application will get the data from the web API, but it will not send necessarily JSON to the browser. It will like process the JSON, make it look like a web page, design the whole web page, and then send the web page out as HTML. Plus, potentially, some JavaScript that the browser would run. Okay? It's the browser who's going to be using frameworks like Angular or React or other things to kind of create this fluid experience in the front. So the browser will show the HTML and run any client-side JavaScript it needs to run to make it a smooth experience. Good so far? All right, okay. So as you can see, the web application's job, all the web application really is it's the web version of the mobile application. That's what it is. Okay, it's just, but it happens that the web application is running on the service provider's side, and just sending out very, and just sending out formatting and content to the browser. Okay, any other questions? Any other questions? Riley? No? You look like you were about to ask a question. Okay. Any thoughts on why we even need a web API? Like, since we're not going to make a mobile application, why do we need an API? Why don't we just have the web application talk directly to the database and we're done? Our life will be easier.
Reveal some secrets
It might reveal, who might reveal some secrets?
from end.
It might reveal some secrets. No, I don't think it will be less secure. I really don't think it'll be less secure. Because the web application, the browser cannot make the web application do anything it doesn't want to do. All right? So I don't think it's a security issue. Modularity? Potentially, it might be nice to separate the content side from the layout presentation side. That's maybe part of it, okay? But if we only have a web application, let's say we knew today we're never going to make a mobile application for whatever reason, okay? Or maybe you're going to make like a I don't know, like a React Native or something like this, or not React Native, but you're going to make, maybe even the browser, even the mobile applications will basically be embedded web applications, right? Who else might talk to an API that I've not drawn in this picture? Who else might talk to an API that I have not drawn in this picture? Yenyu.
Other developers who want to create something.
Yeah, sure, right? Other companies might want to integrate my service into their service in the future, right? Like someone says, hey, I love the application you guys made. It works really well with this, I don't know what, calendaring system we made or something else that we made. We would love to be able to get your data and content into our application as well, and we'll pay you for it, no problem, all right? If you're just having a web application, that'll be difficult because what does your web application give? The content and the data, but also in HTML and all the stuff that your partner organization doesn't need. Your partner organization just needs your data so that they can integrate it into their service or something else, okay? So the web API is also who outside organizations can talk to get access to your database, all right? Well, if they just want my data, why do I need an API? Like if another company says, hey, I love what you're doing, I'd like to pay you some money so that I can integrate your data into our application. Why don't I just give them connection to my database? No, don't do it, professor, you're drunk, don't do it. Why not? Insecure? What is insecure?
You don't know what they're gonna get. They can't have access to everything.
Right, they have access to everything, right? They can read all the things, not just the things that they told you they would read. So that's one issue. And if they have write permission, that's even more dangerous because they could damage things on purpose or by accident, most likely by accident, all right? So you don't want people to have unfettered, uncontrolled access to your database. If a company comes and says, look, I just want some metadata and I'm going to do some analytics for you, then you're like, okay, so you don't need the content my users are writing, right? Well, who's going to control that they're just reading the right things? The API, all right? As we will see later, this kind of an architecture, which I would begin to describe as the beginnings of a distributed architecture, are going to pose big security problems later, right? Why? Our API, when it gets a message, how does it know that the person asking it is authorized to ask it for the things it's asking? Like if the web application, we trust the web application, we should, right? Like if the web application asks for something, we should just give it. But how do we know it's really our web application, not somebody pretending to be our web application? We will soon discover it's very difficult for the API to know who to trust. Who should it trust, right? How does it know that the person talking to it is a mobile application written by your company? Tokens. Okay, so we have to start developing tools to make these different devices trust each other, essentially. Okay, cool. All right. What else did I want to talk about? Okay. A couple of other things, then we'll take a little break. Let's just take a little stretch break quickly. Stretch break. Yes, I love it. All right. Finish. That was a very long stretch. I didn't give you a 10-second stretch. I gave you a 5-second stretch. Okay. All right. So now, in our architecture, most of these things will talk. Oh yeah, one more thing I want to mention. For this week, a couple of limitations. First of all, we're going to start by developing the API in this class. Okay, we're going to start by developing an API. We're not going to make the web application right away. So it might be a little bit of time before you see a web application that you can show off to your friends and your mom and your dad and be like, look, I made it. All right. We're going to make a web API. Is how we're going to start. Second limitation. For this week, I don't want to talk too much about how to make a database. So for this week, we're going to have a simple database, and it's going to be literally just some files on the local server. Okay. We're just going to use the computer's file system as our database. We're not going to use a Rail database for this week. From next week, we will talk about using a Rail database. Okay, so bear with me. So 2 limitations for this week, okay? All right. So we're entirely on the back end and doing it very simply. So between the browser on our application on the API, and any potential mobile application on the API, these actors will all be talking over HTTP. All right? They're going to have content and maybe layout and other stuff in there, but the protocol that's going to wrap the messages is going to be HTTP. Are you okay with this? So let's talk really quickly about what HTTP looks like. All right? So essentially, HTTP is called a request response protocol. And let me just jump back to a previous picture that I had here. You'll notice here in this picture, when I'm kind of talking about HTTP, I'm talking about a client and a server. All right? So when two machines are talking over HTTP, one acts as a client, the other acts as a server, which means that in any HTTP communication, the two ends are not equal. They have a relationship where they each have a role, and they cannot switch that role in the middle of the conversation. Okay? So what is a client and what is a server? Outside of computers, where might you use the word client and server outside of computers? Anybody? Restaurants. Yeah, often the person bringing the food to you is called the server, right? They're serving your food to you, all right? It would be very weird if the server was like putting an order to you, right? I would be like, what? No, I'm the client. Client means the customer, all right? So in HTTP, we have a very strict relationship between in a communication. One person is the client, and the client can only make requests. It can ask for things. And the server can only respond to requests by sending back something. All right? This means that typically the server cannot suddenly ask you a question, right? Your browser can ask the server for things, but the server typically does not ask the browser for anything. The server's job is to listen, and when it gets a request, it sends back a response with whatever the client asked it. All right. That's going to get very old out there. Okay. All right. So between a client and a server, there are two types of HTTP messages. They look very, very similar. But the request, we call it the HTTP request message. And the response coming back from the server is also in HTTP, but we call it the HTTP response message. All right? So HTTP request and HTTP response. All right. And whichever one you're looking at, the request or the response, the structure of the message, of an HTTP message, looks something like this. All right? In the message, whether it's a request or it's a response, the top part of a message will be called the header, and it will have metadata describing what it's about to do, or what it's asking, or what the data is about. Okay? After the header, there'll be a blank. Oh, and by the way, I should mention, HTTP messages are in pure text format. They're just in text. It's not like in a binary format or something. It's in a text format. Okay? So the first several lines, or maybe first many lines, will be headers with metadata about the request or the response. Then there will be a blank line, a line with nothing on it. And then after that will be what we call the message body. This is where the major content of the message is going to be. All right? And I'll show you some examples of this in a moment. In fact, I'm going to show you some examples right now. So let's talk to an API somewhere on the internet and ask it something. All right? For example, GitHub has an API. It's at api.github.com. Oh, question? Is there an error? Is there something? Nothing?
GitHub again.
GitHub again, yeah. You're beginning to think GitHub is like paying me, right?
I was ready to slack you.
Yeah. So, okay, let's talk to GitHub, because it's my only friend, all right? And let's just see let's make a request, but don't tell GitHub this is a nonsense request. Well, let's see what a response it sends back to me to look at what an HTTP request looks like, what an HTTP response looks like, okay? I'm going to talk to GitHub using a little application, a command line application called HTTP. You can download it. It's a really nice application at this website, HTTP. It's called HTTP Pi, actually. Everyone likes Pi, right? So it's called HTTP Pi. It's equivalent to Unix applications like curl or wget. Okay, it's just a friendlier version of them. So, don't need friendly. You're like, I've got the scars to show my curl knowledge. Well, wait till you use this. You might like this a little bit more. Let's see. Okay, so let's see. Such skeptics, my God. So let's send a message. I'm going to use this application called HTTP. It's a command line application you can download from that website to allow you to talk to a web server anywhere in the world using the HTTP protocol. All right. And so I'm going to say HTTP, and well, let me just jump here and do it. Where am I going to do it? I'm going to do it here. So here's what I'm going to say. I'm going to say HTTP, make a request to the GitHub API. All right. What is the request I'm going to make? I'm going to say, just tell me whatever you can about anything you can. I'm actually not going to make a specific request. This little slash at the end is telling it, I'm just saying hello. All right. I mean, I'm trying to get the home resource, actually. I'm trying to access the home resource of the GitHub API. All right. So slash means the root resource of the GitHub API. You don't have to put it. It's by default, there's a slash at the end, if you will. Okay. One more thing, you'll notice I'm putting in a little option called -- verbose. This is to tell HTTP, please show me on the screen the entire conversation. Don't show me like a summary. Show me like every single thing I'm sending it to GitHub and every single thing that's coming back to me. Show me the whole thing. Are you ready? So this is going to be a request and we're going to get a response. Is that a question?
No.
Just adjusting your hairband? Okay. Just okay. All right. Okay. So let's do this. Are you ready? So request and response. So what HTTP is going to show me in a second here is going to be the request it's sending and the response it's getting back. 3, 2, 1, bam. All right. Brrr, what happened? What happened? Two things on the screen. So you see the whole bunch of spaces here? This is telling me these are two different messages. This was the HTTP request message. This is literally the lines of text that my computer, the HTTP application, sent to the GitHub API server. Okay? What was in it? Well, if you remember, I said the structure of a message should be header, like several lines of headers, a space, and then a body. Okay, a space meaning a blank line. All right. Now, if you look at this request, there is no body. It's just several 1, 2, 3, 4, 5, 6 lines of header metadata. There's a blank line, but there's no body after it. Okay. What you're seeing down here is not the body. This is actually the response message that I'll get to in a moment. Okay. So the request I sent, in this case, not always, but in this case, does not have a body. It only has metadata. Okay, why? Because I didn't actually ask for very much. All right. So these are lines of header information, and it follows the structure of an HTTP request. Why? In a request, the first line always looks like something like this. All right. The first line of the request looks like this. If you've not seen HTTP before, please pay attention. All right. The first line says what you're trying, what is the request? It's actually the request is in the very first line. The first word of the first line is saying what do you want to do? And in this case, I'm saying I want to get some information. So I use the word get. It's part of the HTTP protocol. The word get is known to the HTTP protocol. It means you're asking for some resource, some information. Okay? What information am I asking for? After get, you see this little /? Ignore the underline. That's a formatting. It's saying I'm saying I want to get the home resource, the root resource. So slash just means the root resource. Okay? And it says, by the way, the protocol by which we are talking to each other is HTTP version 1.1. All right? There is a 1.0. The next line of the header is, this is still all stuff my computer is sending. It's telling the GitHub API, when you send back the content, the data I'm asking for, I will accept the data in, this means any format. Any format you care to send. */* means any format. We will see some other formats in a moment, but this is saying I don't care what format you send it back to me, just send it to me in any format. JSON, XML, whatever the hell you want. I don't care. Okay? The next line is saying, if you wish, you can compress this information to make it like smaller, and I will decompress it on my side. All right? Connection keep alive. What does that mean? Keep the connection alive. Don't you love how all my questions have a very easy rhetorical answer? It's saying, I want to have a persistent connection. Don't close the connection after you've answered me, because I may have something else I want to ask you, and I don't want to spend some more milliseconds finding your server over the internet again. Okay? So keep the connection alive. All right. All right. Then it's saying, by the way, this is the server I'm trying to contact. API github.com. This is me. This is who I am. It's saying I'm a client. So user agent means I'm a client acting on the behalf of the user. Agent means somebody who's acting on the behalf of somebody. All right. So I'm acting on the behalf of the user. My name is HTTP version 2.1.0. All right. That's an example of an HTTP request. This request doesn't have a body, it only has header information. Let's look at the response from GitHub. The response from GitHub looks like this. Whoa. So once again, it should have headers, and it could have a body. Let's see if it has a body first of all. So this is all header information. Whoop, you notice a blank line down here? There's a line here with nothing, with no content. That's separating the headers from the body. So this response has headers and a body. Okay? Let's look at the headers first. The headers begins with this. It says HTTP 1.1. I agree, we're talking on this protocol. Okay, we're using HTTP version 1.1. What is that? 200 OK. What does 200 mean? It means okay. Yeah. So in the response, the first line starts with the protocol that you agreed to talk with. And within the first line, the second thing is, what was the result of this request? Like, I haven't even, like, not the content, but what happened? Did it go okay or not okay? All right. So what the server sends back is, this is called a status code, HTTP status code. And it tells the client, how did things go? All right. 200 is a status code. And if you're interested in what the status codes are, there's a nice website called httpstatuses.com. Actually, I can go to it. Okay, let's go to httpstatuses.com. 200 means okay. 200 literally means what you requested, I was able to satisfy it. But it also means something a little bit more. It means I was able to handle your request, and I might have something to give back to you. Okay? So 200 typically means everything went fine. All right? Now 200 is not the only status code that means everything went fine. In fact, any status code beginning with 2 means everything went fine. So 200, 201, 202, 203, all of these mean it went fine, but there's some clarifications. For example, 201 means everything went fine, and as a result of your request, I made something new. I made some new information. Okay? I created some new information. So 201 means I created some new information and it went fine. And so on and so forth. I won't go through all of them, but some interesting ones. If everything did not go fine, well, then there's a whole bunch of error codes. The most famous one is 404. I did not find what you're looking for. So if you've ever been in a browser and like your browser suddenly says 404, it means the server is telling it, I can't find what you're asking me for. All right. But there's other error. All the 400s are errors. And they're a specific type of error. It means something went wrong and it's not my fault. It's your fault. All right, so when 404, the server is telling the browser, I couldn't find what you're looking for, and it's your fault. You asked me for something that I can't find. That's your fault, not mine. All right? Other things include unauthorized, means you asked me for something, but you're not allowed to see this. Bzz. Okay? I like 402 is my favorite one. Pay me. All right? You asked for something, but I need money. Sorry. 403, similar to 401. Forbidden means not allowed. What's the difference between 403 and 401? We'll talk about that later. All right? And so on and so forth. Many things. 410, it was here before, but it's gone now. Your fault. Okay? Etc., etc.
What's on a teapot?
Yes, that's your question. I'm a teapot. It says, why are you asking me? I'm a teapot. Here is my spout and here is my... I'm a teapot. They were expecting the IoT age to come, so they automatically put in a teapot. No, I'm just joking. This is just a joke status code that was put into the HTTP protocol a long time ago. Just as fun. Back when the internet was still for fun. Interestingly, in the past 5 or 10 years, a lot of people have said, hey, we're running out of status codes. Nobody uses 418. Can we please change it to something useful? And yeah, actually the standards body said, no, it's fun. Please keep it in. It's the only fun we have in life, okay? So I'm a teapot is in there. But
Does anyone even get it?
does,
How do you get it?
how do you get it?
Yeah.
What do you mean get it? How do you...
see that error, yeah.
You never see that error. Nobody uses it.
April Fool.
April Fools. But it's not too late because now we're in the age of IoT. I'm sure there's a teapot that's on the internet somewhere. And it can reply by saying 418, I'm just a teapot. So we've come a long cycle. We actually could have a use for it one day. Who knows? All right. But it's a joke. All the others are real, okay? So 400 errors means something went wrong. It's your fault, not my fault. There's also a whole class of errors, which are 500 errors. 500, 501, 502. These means there's an error, and it's not your fault. It's me, the server's fault. All right? So you're asking for something I've not implemented, or 500 is a catch-all. It means something went wrong and I crashed, or something like that. Okay? Etc., etc. There's another class of statuses, which are 300s. 300 means you need to go somewhere else. Okay, it's a little bit like, you know, if you like maybe in Tsinghua you go to some office to pay your tuition or something. Where do you pay your tuition? In Tsinghua? Don't tell me 7-Eleven. Where do you pay your tuition? In Tsinghua there's an office. You have scholarships. Where do you pay your tuition?
Actually, I did pay my tuition.
It's online.
They take care of it, and
Remember back in the day? Okay, no, hold on. Where do you get your student ID card? You go to some office, right? Don't tell me online.
You get it on the
Actually, I get my student ID at the police station.
Oh, wow. That's just you, Bishan. I'm just kidding.
That's you, bro.
This is you.
It's in police station.
It's in police station? Fine. You go to the police station. All right? And you go to the police station, and maybe you go to a window and say, hey, I'm looking for my ID card. And they say, you need to go to that window over there. Right? Sometimes that happens, right? Like you go to the wrong person, and they're like, yeah, I know what you're asking for, but you have to ask that other person. That's what 300 means. 300 means you need to go to another window. All right? You need to ask somebody else or something else. So it's a redirection. It's telling you, I know what you're asking for, but you've come to the wrong place, and I know where you have to go to. You have to go here. Okay? Okay. So that's just to briefly tell you the status code, excuse me. All right? So I'm still on the first line. 200 means okay. All right? The rest of these headers are the part of the response, but they're metadata. There are things like, I'm not going to go through all of them. I'll talk about some of them in the rest of the semester. Like, this is how much information I'm going to send back to you. I'm going to send back to you about half a kilobyte of information, about 496 bytes, not including this header. Okay, it's going to be the body of the message is going to have 496 bytes in it. By the way, I'm sending you the message gzipped. It's compressed and sent to you. My HTTP PI program automatically unpacks it, uncompresses it, decompresses it. Okay. Ooh, there's some security stuff in here. Interesting. We'll talk about it later this semester. Content type. So remember when I said I accept any format of data? Content type is saying what format is the data in. And it typically has this style where it's something slash something. The first part says this is application data and it's in JSON format. Okay. It also has, remember this, UTF-8, the encoding format, the data encodings format. Okay. Other things include the date, etc., etc. Okay. There's some other things, e-tags, referrer policies. I'll talk about them later in the semester. But more and more metadata, metadata, metadata. After all the headers are finished, there's a blank line. And here is the actual content of the response, the body of the response. This is actually the data that the GitHub API sends back to me when I request the root resource. Do you see what it's sending back to me? First of all, what format is it in? JSON. And what it's basically telling me is, in this case, since I asked for the root resource, I did not ask for anything specific, it's giving me links to all the places to ask for specific things. It's giving me a telephone directory, essentially. Kind of nice. It's saying, you want authorizations? Go here. You want email addresses? You go here. You want this? You go there. You want that? You go there. Okay? Cool. So it's one big JSON, and that's the end of it here. All right? HTTP request, HTTP response. Are you okay with this? Cool. So we're making web applications. Our web applications have to send back HTTP. So it's not just enough to know like, hey, I'm going to send back some JSON. You have to sometimes fix the headers and do some other things that we'll talk about. Okay. All right, let's take a really quick break. 10 minutes. So 10:30 now, 10:40. Let's get started again. All right. Go get some water, stretch out, do what you wish.